Hey everybody, welcome back to this every other bi-weekly, whatever you want to call it, ExoLife Hangout. My name is Tony Darnell. I run deepastronomy.space. And we are going to have a great conversation today about life in the universe, as we always do every other week, with my usual cohorts. And I'm very happy to have our guest here from Denmark, which I will be introducing in a moment. But before I get started, just want to say real quick that the Deep Astronomy YouTube channel is being sponsored in part this month by the GreatCoursesPlus.com. And if you go to the GreatCoursesPlus.com/deepastronomy, you will get a free month trial subscription for their great courses. They have like over 8,000 lectures and a variety of different things. And I've been watching this lecture series recently called How Science Knows What It Knows. Now, it's really a philosophical lecture, but it goes back to this idea of scientism, which I happen to be currently fixated on right now. And it talks about how science, what knowledge is, and things like that. So I highly recommend that course. Also, these hangouts are an attempt and a collaboration with the Planets Foundation to get the word out about the work that the Planets Foundation is doing, and they have recently finished a Kickstarter. You did finish it, right, Kevin? The Kickstarter campaign. So we will talk, and I'll let. Why don't you go ahead? Let me just pull up my Brady Bunch, my scientific Brady Bunch panel here that I have, and let me go ahead and get started introducing everybody. On the upper left is my guest today, Dr. Tina Santl-Temkiv. She is from Aarhus University in Denmark. Hi, Tina.
Hi.
She's a microbiologist, not an astrobiologist. Is that correct?
Well, I do a little bit of both, but I'm working more microbiology.
Good. Well,
I
welcome.
communicate with astronomers, though.
And do what?
I communicate with astronomers.
Oh my gosh, that's a full-time job
That's
right
a
there.
hard task.
Yeah. Good. Well, welcome to our hangout. In the upper right is Kevin Lewis, who works with the Planets Foundation. You want to talk a little bit about your Kickstarter thing that you just did, and it is over and complete, right?
Yeah, so we just finished another successful Kickstarter to help fund our new live mirrors. And we're taking electroactive polymers and 3D printing them on the back of mirrors to make a specialized mirror that Jeff has been developing. So we had 350 backers. It was really cool to see everybody donate to us.
Yeah, so thank you all for supporting them on their Kickstarter. And the lower in the lower row there was both on the lower left is Dr. Svetlana Berdugina, and on the right is Dr. Jeffrey Kuhn, both of whom work at the Planets Foundation. Hi guys, you want to give us a little brief summary of what you guys, how things are going with the Planets Foundation? And I know you just finished your Kickstarter, but tell us a little bit about what you're doing.
Yeah, we finished Kickstarter. We had first one dedicated to Planets Telescope, the second one to the ELF telescope, and
ELF is the exoplanet life finder, right?
Exoplanet, not ExoLife Finder. Yes,
ExoLife Finder. Okay, exoplanet
yes,
life finder.
And exactly. We had the second campaign dedicated to this telescope to kickstart basically the technology path finder, and maybe Jeff can add to that.
Hey Jeff, how you doing? It's good to see you again.
Good morning.
It is good morning for you. It's evening for Tina.
Yeah,
good night for us.
we are a global community.
We do. We span the globe here at Deep Astronomy.
What Kevin and Svetlana said, I would add that we're broadening the Planets collaboration to embrace the SETI community in Palo Alto. We're in the midst of trying to plan a workshop that will result in a nice snapshot picture of what ELF could do and what it is, and how you can eventually donate towards this very inexpensive but very powerful telescope for finding life in our corner of the galaxy.
Yeah, and I think that the work these guys are doing is extremely important. Now, stay tuned, because it might be, Kevin and I were just talking about this before the hangout, we might try and stream that workshop to the extent that we can here on Deep Astronomy. We're still working that out if it's even possible, but we'd like to maybe try and bring that available to you so you can see what they're talking about, what Jeff is talking about with the collaboration with. Now, you guys are working together, is that right, Jeff? Are you trying to?
No, we are. Jill Tarter is a big part of what we're doing, and an expert in a lot of things that we're not, and I would say that this is an open invitation for those out there in the human civilization to come join with us and figure out whether we part of a cosmic ecology.
All right. Well, let's go ahead and thank you, Jeff. So let's go ahead and get started. We are talking today about finding life in exoplanet atmospheres. Now, we're not talking about biomarkers or indicators of life. We're talking about life in the atmosphere itself. Can we find life in atmospheres? And do we have life in our own atmosphere? I don't even know. So we're going to be talking about that with Tina today. And if you have any questions or comments about our hangout, we hope you'll leave them with us. There's a multitude of ways to do it. The best way is to go on YouTube, watch this, and go with everybody else. With Galaxia, who's already here. Alexander Rangers is here. And a lot of the regulars are already here. So please, you can do it that way. I'm also looking at the Facebook page where this is. There's 2 people watching it live on Facebook right now. I'm sure I'm one of them. So leave a comment there, but I am checking it. And also I'm on Twitch looking at the chat window on twitch.tv/deepastronomy. So please, and I'm also on Periscope, but to be honest, I have to have TweetDeck up to see anything on Periscope. So I hope, welcome. I'm glad you're there, but I can't really, too much going on. Maybe Kevin, can you look at the Deep Astronomy channel and see if there's on the Deep Astronomy Twitter feed and see if there's anybody. If you use the ExoLife hashtag, Kevin will see it and forward it, because he's copying and pasting already questions to us to ask. So, all right, let's get started. So, Tina, you study life in a variety of conditions, obviously, and I guess what I'd like to find out is let's start here on Earth. You said that before we started that you actually use Earth as a model for your studies in exoplanets. So does Earth have life in its own atmosphere?
So yes, Earth actually has quite a lot of life in the atmosphere. Mostly it's microbial life. So we find a lot of bacteria, fungi, and small algae present in the atmosphere. There are actually between 10,000 and 100,000 bacterial cells present in a single cubic meter of air. So, and there is a constant emission of these organisms from the surface of our planet. And this is both from terrestrial environments where we have, exposed soil, particles that get blown up with the wind, or we can have plant leaves, get an aerosolization from plant leaves by rain droplets impacting and then splashing off, getting aerosolized. Then we have oceans where there are waves and small bubbles get entrained, and those bubbles collect microorganisms on their way up, and they will burst once they reach the ocean surface, and then they will eject aerosols into the air. So there is, the Earth is kind of constantly emitting a lot of aerosols, biological aerosols into the atmosphere.
Are these aerosols, you said they're individual, they're cells, they're the microbial cells. Are they actually alive, or are they just organic?
Actually, many of them are alive. So there is also organic compounds getting into the atmosphere, but that's not what I meant. I meant really organisms.
Okay, good. That's what I wanted to clarify. So these little life forms are coming from all over the place. They're coming from bubbles in the oceans. They're coming from, you said, leaves, right? Plant life.
Mm-hmm.
But are these life forms native to the atmosphere, or did they form somewhere else and just happen to end up floating around in the atmosphere? They don't live there. They just happen to be there because of the wind or because of bubbles and waves popping. Do they grow and live and thrive in the atmosphere?
So first of all, we don't know whether this is a passive process or if microorganisms can control this. So kind of, excrete some compounds that make them more likely to jump into the air. In the ocean water, for example, the surface properties could enhance aerosolization. So getting airborne can be enhanced. And we don't know whether bacteria can do that on purpose. Once they are in the atmosphere, we know that very often they are alive. And then the problem that they have is that the air is very dry on the Earth. So they don't have much access to liquid water. Once they get into the clouds, for example, then they are often embedded in these small cloud droplets.
I see.
And there they also have access to food, and they are protected from UV radiation. So that's where they might have some sort of activity, and they may even grow and increase in number.
But again, this is life that has originated somewhere else on Earth and somehow got aerosolized, as you put it, into our atmosphere, where it can either live for a while or it can't, right?
Yes.
Okay.
Yes. So
you said it doesn't have much water. I thought, you know, I mean, obviously it changes depending on where you are over the Earth. Don't we have a lot of water vapor though, as planets go?
Yeah, and a lot of rain, especially in Denmark.
Yeah, right. And here in Florida too as well. So, but those would provide water droplets for them to live in for a while. But again, you don't know if this couldn't be a natural place for life to form. It sounds to me like.
So on Earth, this lower part of the atmosphere called the troposphere is very dynamic. So, you know, you have a lot of drying and then re-wetting. So they are exposed to very changing conditions. And also it's very turbulent. So you have a lot of mixing, and the cells will settle down eventually and deposit back either in the oceans or on terrestrial surfaces. If you have a more violent weather event, for example, a hurricane or a storm cloud that is penetrating more into the higher levels of the atmosphere, maybe in the stratosphere. The stratosphere is much more layered, and then the residence time there is much higher. So
actually, there is a question, one of the questions, how high in the atmosphere life can survive?
So there has been found life forms up to 40 or even 80 kilometers up in the atmosphere.
Okay. So that is the stratosphere, basically.
So it's in the
like
stratosphere. Yeah. Yes. So it's very difficult to evaluate the quality of these results, because usually what we find is one cell that was viable, but how do you guarantee that this cell really comes from this environment? That's very difficult.
So maybe you can explain, how do you collect evidences for life in the atmosphere?
So we use different sampling devices. It's like vacuum cleaners. Basically, we vacuum clean the atmosphere, and then we bring the samples back to the laboratory. And then we can cultivate them or count them or use different techniques. So we have different systems for doing that. So we either collect with ground-based samplers, or we use small aircrafts. So we can go a little bit higher into the atmosphere, and we can collect samples in the clouds and in the dry atmosphere.
But you cannot fly as high as to the stratosphere, so you kind of hope that some of the material was precipitated down from the higher layers. Yeah, that's
like
what you
balloons.
said.
Balloons can do that.
So yeah, there are research groups using balloons, for example. Yeah,
balloons.
Okay.
So an interesting experiment, and I guess the question is, do you know if this has been done, is to take a box of the atmosphere from some miles up and seal it and put it in a condition that simulates stratospheric conditions or troposphere, tropopause, and ask whether or not the organisms survive and can have their own internal ecology to keep going. I think that the question that Tony was getting at, that is on the top of my list, is, can we have a self-sustaining ecology?
Yeah, that's where I was. I was trying to figure that out, if that's where life could actually start and maybe thrive in some way.
So I think in principle this is possible, but there are some preconditions, such as water availability, and then stability of the atmosphere, so that the bacteria can get suspended in the atmosphere and not deposit down constantly. So the Earth stratosphere would satisfy some of these conditions because it's very stable and the deposition is very slow. So in fact, they can get stuck there for years. Mm-hmm. But it's, as far as I understand, very undersaturated with water vapor. So it's quite dry.
Well, it sounds to me like, from what I've been learning about climate change, with the Earth warming up, the temperature of the atmosphere warming up, it's able to hold more water vapor. So who knows? Maybe, at least on Earth, you might be able to get conditions where there's more water vapor, or at least enough water vapor to cover more.
Well, in early Earth, we know that oceans were evaporated at least once, maybe even several times. And a question also one of the participants here, that whether life could be brought to Earth from outside and stay in the atmosphere if on these early conditions when the ocean was evaporated.
That was
and
Galaxia.
Then there was lots of...
You have to say the name, Galaxia. Thank you for...
Galaxia, yes, okay. Exactly. So the question, I mean, we can combine that question that if life could be brought from Earth, and at the time when the ocean was evaporating and the atmosphere was filled with water vapors, kind of in that condition, could survive in the atmosphere, could it or not?
Yeah, I mean, this is, of course, a very speculative.
Very speculative, yes, definitely.
So in principle, it's possible. I mean, life may have originated on another planet in our solar system and get transferred here with meteorites. So that's, in principle, this would be possible. Especially Mars has been indicated as a potential planet where life could have origin. And then, yes, I think life could survive.
Well, Mars doesn't have much of an atmosphere, though. I wouldn't expect to find much in its atmosphere, would you?
No, not in the atmosphere.
Yeah, right.
No,
what about Venus? Cosmic Stardust is asking about Venus.
Yes, Venus.
Could that have some... What, maybe the upper atmosphere, maybe? What do you think of Venus?
Venus is a classical example, I mean, that is often put forward. Because on Venus, there is this funny situation that the conditions on the surface of the planet are very inhospitable. But if you go higher up in the atmosphere, you actually find conditions that are similar in pressure and temperature to Earth. So people have postulated that maybe life could exist in Venus' atmosphere. Of course, there is some chemical constraints. So you have a lot of sulfuric acid in the Venus atmosphere. So the pH in that atmosphere would be very low.
pH is a measure of how acidic something is. So something with a low pH has a lot of acid. With a high pH, it's very basic, not very much acid.
So there's also not very much water.
Yeah, so instead of living in water droplets, they would basically live in acid droplets.
Okay.
Yeah, those droplets, they are 75% sulfur acid and sulfuric acid and 25% of water. So it's not like, I mean, it's a mixture. It's not completely acid, but pretty high concentration, yes.
Okay, so we talked briefly about the Earth, but I want to go, and you, in response to Jeff's question, you said that one of the ways you find it, you get life in the atmosphere, is you go get it, you scoop it up with aircraft or whatever. Were there any, did you mention at the time I was pushing a lot of buttons, so if you said it, please forgive me, remote sensing, ways that we can sense it remotely without going up into the atmosphere and scooping it up to find it. What did you say, what ways there are to do that? And I'm talking Earth first, and then we'll move out to the exoplanets, to other planets.
So
you're not there. We just want to look up from the ground and see if there's life there. Are there remote sensing ways to do that?
So there are no direct methods currently for remote sensing of microbes. There are some ways that you might be able to do that with fluorescence, for example. So shining a specific light wavelength into the particles and looking at the emission. So they would emit another wavelength back. And by the wavelengths that they are emitting, you could maybe infer that these are biological particles, but it hasn't really been done yet.
Okay, so if we look at other planets then, let's say some of the more, it sounds to me like then you're going to be starting when in trying to infer if there's life on other planets with Earth-like planets, right? You want to find planets most like ours because really it seems like you're highly dependent on using Earth as an example to find life elsewhere in an atmosphere, right? I guess, Tina, it seems to me like your job is so much more difficult than most everyone else's, because with just finding biomarkers in an atmosphere is one thing, right? Oh, life could be here, and it could be on the ground, and it could maybe be in a sulfuric acid environment, or as Jeff is fond of saying, could be unlike anything we've ever seen before. But when to find it in an atmosphere, we don't even know. We know life can be on Earth, but we know that we can find it in our atmosphere, but you kind of have to be constrained, don't you, to Earth-like planets in inferring whether there's a life in those atmospheres?
So I don't think necessarily we are constrained. It's just whether these organisms are present in the atmosphere, and whether what is the abundance actually.
I know,
so
but how can you tell if there's organisms in the atmosphere if there's no remote sensing techniques available to you?
They are,
you got to go there, right?
We were talking about Earth's concentrations. Right? So on Earth, even though I said there is quite some microorganisms, we don't think microorganisms live in the atmosphere. But if you had another type of planet where the atmosphere was more stable, and then you had growth of microorganisms in the atmosphere, then the densities would be much higher. So it's basically, it's a sensitivity thing. I mean, what are the densities that you need to be able to detect life on those conditions?
So you're saying, okay, so stability is one thing. You'd like a nice stable atmosphere, something that's not quite as tumultuous as Earth's, and denser. Is that right? Something slightly more dense?
Denser amount of microorganisms. And here we have been talking mostly about the direct detection.
Right.
So you could use, for example, colors to detect them. So if you had photosynthetic
spectra,
in the atmosphere, they would have a spectral signature, and then you could detect them by remote sensing.
But couldn't you do that on Earth too? Couldn't you test your hypothesis by looking at the spectra of Earth's atmosphere, and then go, oh yeah, there's some life. I see it right there. Or
this is definitely the first step. Presuming that there are enough densities in the Earth.
Yeah, I think that I can add here that there were some, in the lab we have experiments to measure spectral signatures, and Tina and I, and including polarimetry, did this. And we study different organisms' signatures and we model them. But for Earth, if you, like Tony says, that this detection is difficult, even from space. Like there were satellites, and there are satellites who look at Earth from space, and they look through the atmosphere, and what they see is the signature of life on the surface. Because on the surface there is so much life that any life in the atmosphere would be overwhelmed by the signal from the Earth, and in the atmosphere there is just not enough density of life. And what Tina says is that I think.
Okay, maybe I don't understand what you mean by density. Do you mean density of the atmosphere or density of life? When you said density, what did you mean, Tina?
Of life, of organisms, yeah.
Oh, sorry. Okay, I thought we were talking about you need something a little more dense, atmosphere-wise.
Yeah, we need clouds made of bacteria, basically. Yeah, and such planets could exist, like. It could be completely different life, what Tina said, or it could be similar life to us, but it would be just so much on the surface that they would prefer to fly to would be overcrowded on the surface by bacteria, and they think like, oh, we want to explore the third dimension, not only 2 dimensions on the surface. That's how animals started to fly on Earth. because they saw opportunity to find more food if they fly, and maybe on some other planets, organisms do the same, and microorganisms find out. And what I like also what Tina said in the beginning, we don't know the reasons for bacteria actually to fly. Maybe they have their own internal reasons for that.
Well, but I think the point that the exobiologists and the evolutionary biologists would make is that to have life in the atmosphere would have to evolve first, or it's much, much more likely to evolve first on the surface.
Absolutely, and we don't talk about evolution.
You need that in order. Well, but of course that's the key point, right? If you had an exoplanet, and you were looking for the signature in the atmosphere, you were tacitly assuming that the life started on the surface, evolved in a pathway that got, because you don't, right? Life requires, for example, surfaces and water abundance and mobility of molecules and things that you don't have in the tenuous atmosphere, where particles much bigger than a micron would fall out. So I think it's important to make the sort of, this is a process that starts on the ground, and the life in the atmosphere is strongly coupled to what happens on the ground.
Yeah, that was the point. I'm sorry. Go ahead, Tina.
Sorry.
No, please go ahead. I interrupted you.
What can be a problem is that there is always some, when you try to detect life on another planet, there are a lot of obstacles. So one obstacle where you are trying to measure surface life is that you might have clouds in the atmosphere. And actually, very often they find that clouds are shielding the planet, so you cannot actually detect that much of the surface or of the biosignature gases in the atmospheres. So you might need to look more into these clouds that are, in a way, disguising other biosignatures. And maybe clouds are revealing extra biosignatures that we can look at.
Okay. Well,
in that sense.
So Cosmic Stardust asked a really interesting question
yes,
this discussion.
Go ahead.
Okay, go ahead.
No, go ahead, Jeff. Go ahead and read it.
I mean, she asked, does this mean that life can evolve in the atmosphere of a gas giant? I think the question is, does this mean that it's unlikely that life could exist in a gas giant if it doesn't have a surface where things got started?
Oh, that wasn't the one I was thinking, but yeah, you guys remember this, right? You watched Carl Sagan in the 70s and 80s. We all remember the ones with the Jovian planets where he hypothesized these big gassy balloon-looking creatures.
Yeah.
Now I can see happening in an atmosphere without this coupling to a surface. Like a gas giant up in the upper atmosphere, thriving on hydrogen, floating around like a big Jovian manatee or something.
Yes, but look, we talked also earlier about that if it can be polluted, and gas giant maybe cannot generate life, but it can be polluted and can survive there if there are conditions for life and there is nutrition for life. So, I mean, like, we don't really say anything. Once we find life, we don't know how it get there and how it originated, and this will be a second question. But life can exist, not originate, but exist in clouds. How did it get there? It can get from the surface or from outside.
Yeah, that's Tony's question, is to get there, right, without a two-dimensional surface, to start with a cosmic mix of amino acids or whatever and get to the point of RNA and DNA. A lot of evolutionary biologists believe that you need a water concentration and a two-dimensional surface to get enough.
Yes, but I said it can be brought from outside. If there is no surface, you can bring life from outside to the clouds of Jupiter-like planets, for instance.
Yeah, and then somehow it has to adapt and be able to.
Yes, and then if it survives there, it doesn't have to originate there, but maybe it can still survive there. This is also an interesting question.
Yeah.
Okay, Tina, I want to get you to Cosmic Stardust question here about, do you, where to go? Oh, well, do you, I don't see it, but I know she asked it. Oh, here it is. Are there any promising planets yet that may show some evidence of microbial life in its atmosphere? Do you have any favorite candidates, exoplanet candidates, that you think have a pretty good chance of having something in the atmosphere?
So I guess that would be a better question for Svetlana or Jeff.
Yes, Proxima B.
Proxima B?
we
Okay.
built ExoLife Finder to look at Proxima B, and we look at surface if there are no clouds, and we look at clouds if there are clouds. So we look everywhere.
So Rob Burnett asked if there's a chance of finding life in exoatmospheres using JWST, and I'd like to take a pop at that and just say that JWST is its best chances for finding life in atmospheres is through transits, which is very rare and very difficult and takes lots of integration time. JWST isn't going to expand our ability to find life very much, and that's what this telescope, this group is involved in, called ELF, is trying to do. From the ground, it turns out we have a much better chance of finding life with the resources that we have than we probably do with something like JWST, which is powerful for other reasons, but not so much for the problems that Tina are talking about, I think. My 2 bits.
Svetlana, do you have some bits there to add? Perhaps.
Well, I think it's good to try, but still, this is only 6-meter telescope, and if one calculates the aperture, how many photons you can collect with 6-meter telescope, it's hard. It's I mean, we should be very lucky if we find something with 6-meter telescope.
Alexander Renders also asked a really interesting question about the tails of comets, which is sort of an atmosphere.
That's right.
Well, what's the question?
Tina, maybe you want to comment on life in comets.
Do we have a chance of finding life in the exoplanet? Sorry, where is it?
In the tails of comets, yeah. If there is any, well, the searches for organic matter definitely exist, and we found lots of organics. But what about life?
I think this is something very exotic. I'm not sure how much water there would be.
No liquid water at all, just ice.
Liquid water, so it would be something completely different. Yeah, not very likely, I would think.
Yeah, well, there was a question on spectral signatures of organisms, and I mentioned that we studied this. There are other groups who study in the labs. We just take organisms, and Tina collected those in the atmosphere. We take them, put them in the lab under reflected light, and study spectra and polarization reflected from organisms. That's what work ongoing.
And capital H asked this question that I think you're trying to answer right now. Are there
earlier
specific
also
signatures?
Before.
Yeah.
Yes. But I also would like to maybe, Tina, to mention that switch to some indirect detection. This spectral detection is kind of direct detection as well. Mm-hmm. But Tina has some really great ideas about indirect detection of bacteria in the atmosphere.
So we are looking at how microorganisms are interacting with the atmospheric processes, because it turns out that all the atmospheric processes and cloud formation, rain formation cannot be explained just by looking at mineral particles in the atmosphere. But you need to perhaps include the microorganisms and biological material, which is much more efficient in developing clouds and rain. So for cloud and rain formation, you need small particles that will condense water, form cloud droplets. And then for rain formation, you need those droplets to freeze. And these biological particles are very good in forming cloud droplets and ice crystals. So we think that they are involved in rain formation. And in this way, they would change the way the clouds develop, the cloud residence time, maybe the global cloud coverage on a planet. And this is also something we have been looking into, the impact of bacteria on clouds and how this could be developed into a global signature in future. Of course, we always have to start looking at Earth and investigating whether this process is relevant for Earth. And then if this is the case, then we could try to detect ways, to find ways to detect that on Earth and on other planets with remote sensing.
So this adds new meaning to the phrase seeding a cloud, I guess.
Yes.
It's very related. Yeah.
Yeah. What I liked that these bacteria create ice, and that actually they are used to in snow making machines on skiing resorts. You know, this is all bacteria which create the snow for skiing. This is really impressive. You know, usage of bacteria.
Wait a minute. What are you saying? That most of the particles that are seeded to produce rain droplets and then ice crystals in snow are actually bacteria and not other inorganic or organic molecules?
That's not exactly the case, but
Svetlana's exaggerating a little bit.
No, the snow-making machines.
Snow-making machines.
Snow-making machines.
Oh, you mean you fill it with bacteria and squirt it up into the.
Yeah.
Oh, but don't tell the military about this.
It's a commercial product called Snowmax that they are using. It's very often used in European ski slopes.
Just don't breathe when you go through the snow.
And it's a bacteria-based product?
Yeah. It's a plant pathogen bacteria. They use they have these proteins that are very efficient in freezing. So it's ice nucleation activity proteins. And these bacteria use proteins to damage plant tissues. So the plants leak food that the bacteria are growing on. So this is something that they use in their terrestrial environment. And then it looks like they might use it also once they get airborne and get into the clouds.
Okay. Well, let's talk a little bit about the limits to the complexity of life that can be in an atmosphere. We've talked about how they get there. It sounds like, from what we've learned, that there is some kind of, at least for now, a two-dimensional surface involved that gets them somehow aerosolized into the atmosphere. We've talked about leaves. We've talked about bacteria, several cells or more. Is there a limit to complexity? Now, I've heard, I don't know if this is true, but in Florida it can actually rain fish. So I've never seen it. I've only heard tall tales, but maybe somehow they get evaporated and the big dump will rain fish down on things. But of course that's a temporary situation, and they didn't evolve up there. They just got grabbed from there and got thrown around by some strange process. Do we have any idea, or do we even want to speculate on how complex this life can be? The density of the life, you said, is an issue. I think the density of the atmosphere is also an issue. That might mean heavier things can live up there, right, Tina or Svetlana? I mean, you can have heavier things in a denser atmosphere.
Yeah, tardigrades.
Tardigrades. Those sea cow looking, yeah, those scare me. I don't want them in the atmosphere. Do they rain tardigrades in exoplanet? No, seriously. What about the limits of the complexity? What can we have? Carl Sagan showed us that we could maybe have these gigantic air balloons floating around that look like jellyfish, but they're really in the atmosphere. Svetlana says tardigrades can be up there. Is there a limit to the complex?
Well, I said that life could find out a third dimension for whatever reason, like birds did. Okay, so now the question, I mean, what's the question? Birds live in the atmosphere, okay? They fly there.
I don't know. Living in the atmosphere is the right way to say what birds do.
Yeah, they explore it.
They could spend a lot of time up there, but I don't think they live up there.
Pelagic birds live for days and weeks without landing, right? So
and
there is an expansion.
Can do it too.
Yeah, exactly, right. But I think the point is that the evolution process has to take place on the ground.
That's what it sounds like, yeah.
And then, I mean, it's like amphibians or creatures that live all their lives except when they have to reproduce, and then they go out and get into ecological niches where where they have a
Yes.
greater success
I
story.
imagine on Venus, if life ever existed on the surface and you know and got too hot on the surface, then somebody who wants to survive learn to fly, you know, and learn to stay in the cloud. So I think life is pushed by environmental conditions to adapt. We know that it's very adaptable. And we can imagine a condition on the planet that it's originated on the surface as it required, but it just became inhospitable on the surface and they moved high up, you know?
Yeah, because they're not living there. You know, there's,
I feel like, yeah.
We're talking about life in an atmosphere.
Yes.
I get that they've adapted to use the third dimension, but I don't buy that that's life that lives in the atmosphere. And I would need something like even monarch butterflies. They spend, you know, what is it, weeks or months traveling their distance, but even they land in the course of their migration. So I don't know.
I'm with Tony. I think you got to have the life cycle is such that
let's see what Tina said.
We're talking about life that can exist solely in the atmosphere. Doesn't have to
well,
land.
It can origin somewhere else, but it moved to the atmosphere and lives just there. Is it possible?
I would say it would be limited, very likely, to one unicellular organisms. So very small organisms that can, you know, take up organic matter from the atmosphere, maybe in volatile form, and then sustain themselves in small droplets. Mm-hmm. Because even if the density of the atmosphere was higher and you could keep bigger organisms suspended, I mean, they still often will feed. They need a food chain. So they need other organisms to live from. And while microorganisms, they can take up organic vapors and they can sustain on those. And atmosphere has a lot of organic matter.
You know, a really promising exoplanet or exomoon that I think would be a good candidate for some of this is Titan. Do any of you guys know? And this is where I know that the Huygens probe went down and landed. Did they scoop up any of the atmosphere on the way?
Well, that was the lander before.
Yeah, that's what I'm talking about. The lander, the Huygens lander.
Yeah, yeah. Well,
do you know if it scooped up on the way down any of the atmosphere? Because that's a direct sampling there.
Yeah, it did analyze the atmosphere and then ended and analyzed the surface and it was. I mean, this.
But in that sampling of the atmosphere,
so the probe of the atmosphere.
Did they find anything?
I don't think they would be able. They measured the chemical composition, yes, but not. They couldn't be. There was no experiment on saying if there is life there.
Oh, okay.
I don't think so.
Okay.
There are ideas and a lot of scientists who are interested to send a lander to Titan Lake and do experiments to search for organisms there. But you need special experiment for that.
Okay, well, let's get to Andrew Planets. Let's get to some questions here. Andrew Planets going, and by the way, it's good to see you again, Andrew. I'm glad you're back. Would photosynthetic life that has evolved to exist at a specific air pressure on Earth also be able to discharge the air pressure needed to breathe in a sealed area, as in living quarters on Mars? I don't understand that question. Would synthetic life that has evolved
like cyanobacteria, I understand. If cyanobacteria would be sent on Mars, would they produce oxygen for other in a sealed container, let's say?
Oh, is that what he's saying?
I guess so.
Specific air pressure on Earth also be able to discharge the air pressure needed to breathe in a sealed area, as in a living quarter. I'm sorry, Andrew, I don't understand this, but yeah.
Well, isn't it about, can we use these ideas for life in Earth's atmosphere as a mechanism for making an atmosphere as needed for the.
Well, we could make atmosphere on Mars in a sealed environment. I'm sure using bacteria and plants and.
Well, that's what plants
which
do,
produce oxygen,
and that's building or reconstructing the ecology to make things breathable for humans is probably one of the major
Yeah, there is an
mechanisms.
experiment in Arizona called Biosphere 2. 2, because the Biosphere 1 is on Earth and 2 is on the sealed container. This is a big construction where they did experiment where plants were used to maintain the atmosphere, not produce, but maintain the atmosphere. So the oxygen was pumped into that building, and then there were efforts to maintain the atmosphere with plants.
Okay, and Yurik Mazino, Deep Astronomy, if the atmosphere is dense enough and organism has a low enough density, it doesn't matter if we call it atmosphere. For all intents and purposes, would it not be most like marine life?
It does matter if you call it an atmosphere, because the density of energy, the density of organics, the density of the things that you need, life requires energy. And so microorganisms take a lot less energy, and then there's a potential, I think, as we were talking, for making life self-sustaining in an atmosphere, even though it hasn't been proven. But the idea of the analogy of the marine environment, just because things float around in the ocean, is very different because of just this 6 orders of magnitude, a million times difference in densities, and that factor of a million for
Well, yeah, and I guess that's why I was going back to this idea of density of the atmosphere and I guess buoyancy, right? If you can remain buoyant in a medium long enough, you might be able to evolve in it. If you can somehow be buoyant. So
yeah, that's
why I always
Carl
thought the
Sagan
density
suggested those jellyfishes.
Yeah, exactly.
I think the biggest difference would be liquid water in this case, because you don't have a solute in the atmosphere as you have in
you don't have, I'm sorry, a solute, did you say? Solute.
You don't have a liquid environment. In a way, it's similar because it's mixed and it's dynamic and things are suspended. But on the other hand, you don't have a liquid environment.
And that's why you were saying at the beginning, this water vapor is so important.
And our idea of life is that it's connected to liquid environment. At least life as we know it, liquid water.
Yeah. And so at different pressures, other things become liquid. So maybe again, if we had a liquid methane like in Titan, I don't know. I just wonder about. I think atmospheric density and, as you said, stability early on is going to be huge if life can just somehow come about without the need for a surface or even a liquid like an ocean. So. I don't know. It'd be a weird kind of life, that's for sure. By the way, Yurik, I just want to mention real quick. I need to get with you again on the Discord chat that you made because I want to use it now. So I know you made it. So at some point, I don't know. Let's chat about setting that up. I just recognized your name and I've been meaning to reach out to you. So I want to set up a Discord chat for some events. So. That you set up for us. Okay, Rob Burnett, what is the best way to go about finding primitive life on exoplanets, ground-based colossi, or space-based telescopes, breakthrough starshot, etc.? I think this group, Rob, is a little bit biased about that question. You ask them the best way to find life, and these guys are working on a colossus, right? So go ahead, guys. What's your best bet for finding life?
I think there's a really good way of answering this, and it's just one. It's 2 words: diameter to the 4th power. How many words is that? That's more than 2 words.
Diameter to the 4th power.
4th power. That the ability to detect the remote sensing signals that Tina and Svetlana need to see these biological markers, and to extract that signal from the background noise. Is something that improves like the diameter to the 4th power of the telescope. So that means that if you can double the diameter of the telescope, you get 16 times more sensitivity in being able to see these signals, these biomarkers that we're talking about, oxygen or ozone or chlorofluorohydrocarbons that tell us that the atmosphere is polluted in the same way that we would do it. And that's why from the ground, we're so much better able to find these signals, because from the ground we can build telescopes that are 100 meters across with new technologies, And we can build them especially to find and extract the signal out of the noise. And from space, we're stuck with telescopes like JWST. Now, JWST has
told you they were biased, folks. I told you.
It's not biased. It's that,
it's just
that
true.
JWST is
It's
6.5. It's 6.5 meters, and it's a fantastic telescope for enormous pieces of astronomy and looking backward into the universe. But it isn't going to do the exolife problem. We are going to see life. Somebody else asked, Jay Goss asked, are we going to see life in the next 10 or 20 or 50 years? And I think we're going to see life, exolife, within the next decade, for sure, if we can get over this barrier of building telescopes to do everything, but yet build something that is pointed at and developed to do the exolife problem.
Well, I would like to add here that at this point, there is no much, well, there is still small difference, but not very big difference between quality of measurements in space and on Earth. We did learn how to deal with the Earth atmosphere. And we have 10 8-meter telescopes on Earth. We didn't find life yet. So how can you imagine with a similar size telescope, you go to space and you find life?
So Tony's probably tired of hearing us say this, but space is great because we can get rid of the atmosphere over a wide field of view. But with what we now know, we can correct the atmosphere. So the twinkling effect and the resolution. Space is unavoidably great for looking at wavelengths where the atmosphere is absorbing.
That's right. You're not convincing me that you've managed to somehow see infrared wavelengths from the ground that are simply blocked.
But the atmosphere.
Sorry, but JWST is going to be looking at wavelengths you can't see. And
exactly. But the life problem, the exolife problem, doesn't depend just on those particular wavelengths. And there are windows in the atmosphere at 10 microns, at 5 microns, at 2.5 microns, at 1 micron, where the atmosphere, it's a little bit absorptive, but that amount of trouble that we get for that small absorption is hugely balanced by the ability to make really big things. Remember this, the same telescope in space compared to on the ground costs at least 100 times more.
Mm-hmm. No.
Okay.
And Jeff, you had me at, we're going to find it within 10 years. Okay. So I'm with you on this. I think that when it comes to finding life, you guys are dead on. You're right. You've got the advantage. You've got the instrument that is specifically designed to find this thing. But don't tell me that you've solved the atmosphere problem, because you haven't. And when you start getting the first stars and galaxies through your ground-based telescopes, then you can come talk to me about it. But you can't, because there's too much the atmosphere in the way at those wavelengths to see them. So that's all I'm saying. You guys are right, though, and I'm extremely excited about this ability, this finding life business. Now, you're going to find it probably within the galaxy, right?
Yes.
Oh, very close. Right. There's a few hundred stars that we have to look at.
Yes. So
that are within the reach.
Other galaxies, maybe Andromeda, other places would be ideas.
You'd have to depend on these other ideas, right? The optical or otherwise. Mm-hmm. And the atmosphere is a place, right? The atmosphere is the key thing that we want to be able to look at, and either the markers of life or maybe a weird place where the clouds are made of E. coli. Who knows? I think that the point here is that usually our understanding is very much limited by our imagination.
I think all this discussion about clouds and life in clouds, it's interesting from the point of view that many planets will be in clouds, and the ideas what we discussed today actually imply that it's not completely lost case if planet is in clouds. There could be some signals of life in cloud.
Okay,
yeah, that's a general problem with biosignatures. It's not that you want to say other biosignatures don't matter. It's great that we have gases in the atmosphere as biosignatures. We can use oxygen, we can use ozone, nitrous oxide, whatever, trace gases. But I mean, you don't know if this will be enough. A lot of biosignatures give false positive, where you think this is result of life, but it's not. And you need several clues to be more sure. Then you have clouds that are preventing you to see the gases in the atmosphere. So I agree with that. I think it's nice to have several biosignatures available once we get so far with the observational possibilities.
Okay.
Yes. This is the last question is great. I love it. How many meters ground telescopes could we build for the price of JWST? No, it's $9 billion. So we could build 18 colossi. 18 colossi.
You've been waiting for that, haven't you, Svetlana? I can just tell. Coupled with the fact that JWST has been delayed now till next year, I think the case can be made that a lot of good science can get done sooner if we built ground-based telescopes. I just want to say for the record, I love ground-based telescopes. I use them all the time. And in fact, but I just don't want to say that they are obsolete quite yet.
No, you are right.
There are quite a bit of things they can do. Albeit,
of course,
admittedly,
X-ray,
for a lot of
gamma
money,
ray,
and I'm not going to sit here and
UV.
tell you that it's worth it, because to me, one Hubble Deep Field is worth $9 billion. I'd pay that much for it, but that's me. I'm not a value shopper. Okay, I don't.
We don't need 9 billions. We just need $500 million. That's it. It's just a little piece of it.
One image of the first star in the universe is worth $9 billion to me. I'm sorry, it just is. I'll take it. Or the very first galaxies.
I completely agree with you. Right? I mean, JWST and the TMT and the ELT they're all going to change our perspective on life here on Earth. That's why we do it. They're going to put us in the universe in a way that we never understood, that may somehow increase our survivability. But even more important than that is to put ourselves in the biological world, or the ecology of this part of the galaxy. There is an ecology out there. I'm convinced of it.
Yeah.
And we're blind to it. People keep saying, well, we haven't found anything. Well, because we don't have the sensitivity to find something. And the parameter space is so large in radio. But we could. And for a fraction of the cost of a JWST, we could build a telescope that goes well orders of magnitude beyond JST, and being able to find the biomarkers that Tina and Svetlana are talking about.
Yeah, and the point that you all are making about this, and I agree with you, that these general purpose telescopes they're expensive, and they're limiting, and I think that era might be coming to an end, because we do need to start thinking about what problems do we want to solve and what instruments do we need to solve them. And I think that the Planet's telescopes the Planet's Foundation's telescopes are certainly a step in that direction, where you've just decided, look, is there life out there? What are we going to take to find it? Let's build the thing and let's look for it. No, it's not going to be good for finding the first stars and galaxies. That's not what it's built for. It's built for finding life. And so I think you're right. You've made an excellent point there that I can't begin to argue with. And there are and in some ways, ALMA is like that. ALMA is a special purpose. It's not, it does amazing things, but it's designed to look, there's a whole range of scientific problems it can't solve, but yet it's still absolutely worth building. So, I take your point, and I agree with you. These general purpose telescopes, I think, are a dying breed, especially on the ground. So, with that, do you want to comment?
They're not, but they're different, right? They're big questions, they're big problems that we have to answer, and then there are all the littler, I don't mean little in a pejorative sense, but there are enormous numbers of other associated questions that help us phrase and interpret the other questions. It's part of this, right? There is an ecology of instruments somehow that's needed to address the questions. And right, that when the first Keck telescope happened, it didn't blow open all of astronomy, but what it did do is stimulate the understanding that we needed many more telescopes and many more tools to be able to understand and answer the questions that were created by this first glimpse. And we get our foot in the door, and we start to open the door, and there's a whole new room out there with things that we can't yet begin to imagine. And it's important because it puts our place in the universe. It gives us our perspective, and that's what we're doing. That's part of our survivability, is knowing that perspective.
Okay, I want to end this hangout with Joe Schmo's question, and I want to start with you, Tina, and then I'm going to get everybody's response to this as well. How resistant do you think society would be to accepting exolife when it is definitively found? Now, there's two things there. Do you think it's going to be definitively found? And what do you think society will be like? What do you think will be resistant to accepting it? This is speculation, Tina. No one's going to hold you to this. But what's your opinion on how resistant do you... First of all, will we find life elsewhere? And how resistant do you think we'll be once we do? Are we going to be in denial?
I think we will find life elsewhere eventually. I don't know if it's going to be in the next decade, but that's another question.
I trust you.
But I think the society will accept it as long as it's not too close to us, maybe.
Yeah, because as long as it's over there and not in our backyard, right? Okay. Svetlana, what do you think?
I think that we will find life, and we find it soon. As soon as we have our telescope built, we will find something. And well, I'm optimistic. Of course, we can, in the beginning, look only at few planets, and it's not necessarily life is there. But as we build up telescopes, we will find something. And for the society, I do hear concerns, people afraid of it, yes. And
even Stephen Hawking said he was, right? He didn't want to, he thought it was a bad idea to be advertising that we're here.
Yes, but if we find it, it's not necessarily we advertise it ourselves, we find it passively. And so there is no need to be afraid in that. We find it passively. So that is, this is not actively sending signals. Of course, we will be very tempted to send signals when we find a life, and this is another concern we have to discuss. But I think it will be exciting, and society maybe will be divided. Our society always divided. So on any question.
Yeah, that's true. That's very true. Jeff, what are your thoughts on that?
You know what I think.
I know.
Look,
tell us if NASA's going to hide it from us or what. Imagine you wake up tomorrow and you see in the New York Times, and it's not fake news, that a life signal has been detected on a star which is 20 light years away. I think for part of our population, the immediate response is we're not alone in the universe. Life is not so rare and fragile. And gosh, maybe the pessimism that some people have, that we're going to wipe ourselves out, or that life is just a singular development that goes away. Now we see an example, and it's not far away, that life that there is some kind of ecology that exists beyond our planet. I think that's a day that we can hope to see within a decade, within our lifetimes. Okay, but how resistant do you think we'll be to the idea? Are we going to freak out? Are we going to be like dancing in the streets? What's going to happen? What do you think? How resistant?
Well, there are always those Krishna people.
I'm not going to join the Krishnas, but I'm going to dance in the street because it means that life isn't so fragile. I'm going to be much more optimistic that the insanity, which is the human race, is a temporary state, and that
what's going to happen, right? There are going to be people out there going to say NASA's going to hide. We've already discovered life, but NASA's hiding it. I love those, the conspiracy
Area
theories.
54. Right?
Yeah. So,
well, we find some. It's not when I find life, not necessarily intelligent life. Okay, this also must be different. So we'll most probably will find a primitive life, and maybe not everybody will be dancing for that, but I will be very happy.
It depends on the context of finding that primitive life. If we find it next door, I'm not dancing in the streets. But because we talked about that with great filters. But if we do find intelligent life, I might dance in the street there. Or if we find primitive life that's possible, maybe somewhere 50 light years away.
Well, let me ask you a question, Tony. Then what happens? What happens? So Starship is. Breakthrough is interested in doing in situ probes. What happens if Breakthrough goes to Proxima B? They put a little PCR machine on the star chip, and they do a sequence of life that's found in the atmosphere of Proxima B, because it can somehow pass through the outer atmosphere before it blows up. And then they send back a genetic sequence, and they find out that it has the same amino acid content as life on the Earth. Then what do you think?
Well, it depends. Is life there? The amino acids doesn't equal life. The building blocks of life doesn't
Well,
equal
okay.
life. So
They find DNA, and the DNA looks like that it's
then that's
coated with the
encouraging
same.
because it means life is hard. It means that even though you have all of the building blocks of life, it's sitting there. You can build all the life you want, but you don't have it. It means that you've got it's hard. It's not an easy thing to do to go from those amino acids to life. And that means life is rare. That means you may be wrong about finding it in a decade. And that also means that we have already passed that great filter because we have gotten over that one hurdle. We maybe have others ahead of us, but that one we've gotten past. So amino acids, but no life tells me life is hard. Otherwise, we'd have it everywhere. But if we find it there, and if we find evidence of life on Mars, then we've got a problem. That's what I'm saying, because it's everywhere.
No, the great filter theory has a problem, I think.
Okay, well, we should. Kevin, note to self: we should make this. We should continue this discussion in another hand. Okay.
Sounds good.
All right, guys. I want to thank everybody for commenting. I did see you, by the way, on Facebook. I can't pronounce your name, but you're from Nairobi, Kenya, and you wanted to know if what if other forms of life exist, but they are not organic in nature. How are you going to detect it based on your known signatures? We talked about that at the beginning, where we discussed remote sensing of these things. So please check out the beginning of the Hangout, and we will answer that question there. Thank you all so much for watching. Tina, I want to thank you so much for being a part of our Hangout. My guest today was Tina Santl-Temkiv. She's from Aarhus University from Denmark. Thank you for taking time out this evening to speak with us about life in atmospheres. And we hope that as your work progresses, you might consider joining us again.
Thank you.
Thank you.
All right.
Hi, Tina.
Thank you, guys. I want to thank you all so much for watching. And, let me do this. I have to do all my little button pushes and this, that. Thank you all so much for watching. And as always, keep looking up. Okay, that is it.